Hi, I'm Nicholas, and this presentation is about gamma correction. This is the agenda. The first topic is what is gamma, then how color is affected, what is gamma correction, what happens with image files, what is sRGB, when should I worry about all this stuff about gamma correction and gamma. After that, we will see some examples of things rendered that are gamma corrected versus others that are gamma uncorrected. Then how can we solve these problems, a conclusion, and after all that stuff, I will show all the references that I used to learn about this topic. As you know, to display an image in the monitor, you need a voltage applied, right? That's the first thing we need. That voltage that is applied outputs a slight intensity in the monitor screen. In a perfect world, the input signal will be equal to the light intensity, but this is not true. The monitor response is something similar to this curve. It's an exponential curve, and the exponent of this curve is what we call gamma. To see how the color is affected, we will begin with this example. This is a linear ramp. It's linear because it's easy to distinguish each step. In these 10 steps, you are going from black gradually to the white color. In this case, a gamma curve of 2.2 was applied to the first linear ramp. And as you can see, it's difficult to distinguish the dark colors, but it's easy to distinguish the white colors. In this case, an inverse gamma curve of 2.2 was applied to the first linear ramp. And in this case, the opposite is happening. Basically, it's more difficult to distinguish between white colors, but easier to distinguish between dark colors. An interesting thing that you can see here is that in the three cases, black colors are still black, white colors are still white, but the colors between them are shifted. In this case, it's more difficult to distinguish dark colors, and in this case, it's more difficult to distinguish white colors. And of course, for mathematical reasons, if you apply to the first linear ramp a gamma curve of 2.2 and then apply the inverse gamma curve of 2.2 to the resulting image, you will get the original one. To see another example, here we have a square which has RGB values of 0, 1, and 0. This is like a total green color. In this case, if we changed 0 for 1, you will get the white color, obviously. As you know, the RGB values, floating point values that go from 0 to 1 are mapped to integer values from 0 to 255. So if you have the RGB color 0.5, 1, and 0.5, you will expect to see this RGB color in the screen because 127 is the 50% of intensity than 1, that is 255. But you will actually see something different. You will actually see this value, a color that matches this value. That's due to the nonlinear monitor scale. If you are using a typical gamma of 2.2, that means that a pixel, in our case, the R and B channels that we were using the 0.5 value, the 50% intensity doesn't emit the 50% of light, but something that is near the 22%. Okay, and what's gamma correction? Given that monitors are nonlinear, then we need to apply the inverse of the monitor transformation before the pixels are drawn or are shown in the screen. This process of applying the inverse of the gamma of the monitor is called the gamma correction. As you can see here, this inverse gamma cancels out this one, so you get a linear result. For example, if we are using a CRT monitor with a gamma of 2.2, the gamma correction will be the inverse of the current gamma of the monitor. And in this plot, you can see that blacks remain blacks and that white remain white. So what happens with image files? Why are they displayed properly in the monitor? Suppose you have your camera and suppose you take a picture of the moon, then the RGB channels are not stored directly in the image file, its value, but instead a gamma, 1 divided gamma, is applied to each RGB channel before storing in the file. So your result are RGB colors gamma corrected. After that, when we want to show the image in the screen, the monitor applies a sRGB correction to your colors. So basically it applies its gamma and the result is linear. What is sRGB? sRGB is a standard RGB format that was created by HP and Microsoft to be used, for example, in monitors, in printers, and in image in the internet. It is pretty similar to the gamma 2.2 curve. You can see in this plot that they are basically the same. But for example, if you see two images that are corrected using in one case sRGB and in the other one gamma 2.2, you will note some difference. sRGB in the case of DirectX was used first in DirectX 10 in 2008. But for example, PS4 and Xbox One have the same high quality sRGB than the current PC generation. CRT monitors and LCD monitors also supports this standard. But also CRT monitor that doesn't support it have some circuits that adapt all this stuff to be working properly. PS3 does sRGB better than Xbox 360. Xbox 360 has a really terrible approximation of sRGB. As you can see, it's not linear, but it's far from being similar to the PC gamma curve. Okay, I was talking a lot about this, but when should I worry about all this stuff? Because if you simply use image files that you have in your hard disk to be displayed at the screen, then you don't need to worry about it. Because as we saw, the image file is storing memory with the inverse gamma applied, then the monitor will apply the gamma and you will get a linear result, which is correct. But for example, if you are a graphics developer, you should know that most render engines and graphics API work in linear space internally. So they assume all the data that is sampled or used is in linear space. As we saw, texture images already are gamma corrected. An exception to this rule are HDR images because they are stored linearly in memory. Then what it means that the resulting image has mixed elements because in this case you're working with linear data and in this case you're working with gamma data. So for mathematical reasons, if color values are added and both of these values were gamma corrected, then we can represent each value like this: a color raised to inverse gamma plus another color raised to inverse gamma. That obviously, for mathematical reasons, is not equal to this, to work first linearly and then raise to the desired inverse gamma. And for example, in that case, you are going to double the gamma on the texture. So your render target will look washed out. Some ways to detect this problem in runtime when your application is showing something in the screen is that smaller textures that are distant will appear noticeably darker than the larger ones that are near the camera. Also, image quality compensation by adding more light and shader tricks. You can know that, for example, your scene has a lot of light, but you need more, and you need to do some tricks in shader to get a correct result. That's a hint that should tell you that something wrong is happening. Also, for example, when you change a nonlinear input, and it is, for example, it's brightening or darkening by lighting, if color tones change, that's another indicator that something is happening. Okay, now we will see some examples about gamma-corrected versus gamma-uncorrected renders. In the first case, we can see that uncorrected textures and an uncorrected render target was used. In the second case, uncorrected texture were used, but the render target was gamma corrected. In the third one, we used gamma corrected textures, but an uncorrected render target. And in the last one, both things were properly gamma corrected. In this one, you can see how this gamma corrected example looks versus this one. Here, dark colors are difficult to distinguish, but not here. This example is an example of a skin technique and subsurface scattering. This is the gamma corrected one, and this is gamma uncorrected. You can see all the extra light in this picture. In this example, you can see that no gamma correction was applied on textures that were used to render this. And in the right, we were working with gamma corrected textures. Okay, a good question is how can we solve these problems? First of all, you need to load image formats that are in Gamma 2.2 or sRGB space. For example, DirectX and OpenGL has texture types that are of sRGB type. So in this case, you should use them. DirectX and OpenGL basically read this texture data through a shader sample. If the texture is in this sRGB space, then it is converted to linear space. That is basically the space we need to work. Basically, it's doing this. All the stuff I mentioned in the previous slide obviously only should be applied to textures that represent colors, like texture mapping. But for example, normal maps, displacement maps, and light maps that store different information than colors in its pixels shouldn't be use the sRGB format, because otherwise when they are converted to linear space by the shader, you will get wrong information. In this case, for example, this is a height map and this is a normal map. Obviously, they have colors, but these colors in the meaning of a color is not the information that we need. In the case of a normal map, each pixel represents a normal, and in the case of displacement or height maps, each pixel represents a height. Also, you should use sRGB format for your final render target, because remember that you're working in linear space. But then you should apply the gamma that will be cancelled out by the monitor and that will be finally displayed as linear. Otherwise, you will get wrong results. In the case, for example, of DirectX and OpenGL, you can also set the type of your render target, that is basically a texture, as an sRGB color format. And obviously, you should avoid the previous tip with your intermediate buffers. For example, the buffers that you use for shadow mapping or post-processing shouldn't be in the sRGB format, because you are storing linear data there, not sRGB format data. Otherwise, of course, you will get wrong results. So, this is basically the process. You store your textures in sRGB color space. The shader, through the sampler, converts this data from sRGB color space to linear space. You work there, and then the rendered output converts each linear space data to sRGB color space. Another good thing to assume is that the user doesn't know about gamma correction, monitor calibration, the gamma corrected textures, and all that stuff. So you should provide something like this, so he or she can manually set the correct gamma values. Because, of course, current gen monitors are, all these monitors convert your data to a certain gamma, but not all of them have the same gamma value. So, conclusion. Proper gamma correction is probably the easiest and most inexpensive and most widely applicable technique for improving image quality in real-time applications. Because, as we saw, it's a matter of deciding the correct texture to use. Even if you want to avoid sRGB gamma curve and you want to use the gamma 2.2 curve, you are going to only add some floating point calculation in your shader that shouldn't be expensive. And the image quality, of course, if, for example, in your render, to render a correct scene, a good looking scene, you use a lot of lights and hacks because your render engine is not gamma corrected, then if you follow the different hints we saw, you are going maybe to see a terrible image as a result. But that's due you did a lot of hacks and added a lot of unnecessary lights and tweaked a lot of unnecessary light parameters. So instead, another conclusion is that instead of ignoring it and use light parameter tweaks, light addition, shader tricks, and other hacks, you should implement a gamma corrected pipeline. These are some web pages that helped me a lot to understand all this gamma correction stuff. This is the end of the presentation. Hope it was useful for you. This is my personal blog where I post things about programming. And if you have any question, please post below this video and I will try to answer them in the more correct way I can. Thanks.